All right, we are continuing our discussion of fluids and specifically pressure, and that brings up the idea of gauge pressure versus atmospheric pressure. So if you put an air gauge onto, let's say, your tires in your car to measure the air pressure in the tires, that is actually measuring what's called gauge pressure. So that is just the difference between the pressure in the tires and atmospheric pressure. If we wanted to know the true total amount of pressure in those tires, it would be the gauge pressure that we measure plus the atmospheric pressure that is acting all around it. That gives us the total amount of pressure. So absolute pressure is the sum of atmospheric and gauge pressures. So one engineering application of pressure can be found in Pascal's Principle. So the thing about a fluid is that if you have fluid throughout a system, through a series of pipes, whatever the pressure is over here is going to be the same pressure over here. The pressure in a fluid in a confined system is constant throughout. So if we can take a small piston with a small area and apply a force to cause a pressure here, the same pressure is going to come out the other end, but if we apply that pressure to a large area, we can get a large force. This is called a mechanical advantage. So simple machines like levers and screws and pulleys and things like that also give us mechanical advantage. So Pascal's principle is a way that we can use pressure in a fluid, like hydraulic fluid, to gain mechanical advantage. So you probably have hydraulic brakes in your car that take the pressure applied by your brake pedal and amplify it to produce a much greater force acting on the disc or brake rotor. Hydraulic lifts can lift cars, barbershop chairs, all sorts of things can use this hydraulic pressure mechanical advantage. So here's Pascal. I've not exactly photoshopped, it's more crudely cut and paste his head onto a mechanic to illustrate the mechanical advantage gained by Pascal's principle. But the essence of Pascal's principle is that the pressure out equals the pressure in. The pressure throughout the system is constant. Okay, and so pressure is equal to force divided by area. So F out over A out equals F in over A in, right? And so if we just kind of switch these places, or I guess actually move the F down here and the A up to there, that's more like it. What we're saying is the force out divided by the force in is equal to the ratio of the area out over area in. So like that image with the car lift, if we have a large area on the out, so we've got a small area in, large area out, that means for a relatively small force in, we get a really big force out, okay, just by changing the area that the fluid acts against. So some tools that we can use to measure fluid pressure. This is an example of an open tube manometer. And so if there was zero pressure here or zero pressure difference between the two open ends of this tube, then the levels of fluid would be equal to each other. But if there is a pressure differential, then the higher pressure here is going to push this fluid down, and it's going to have nowhere else to go but up. And so we get this difference in height. And this difference in height of fluid can be used to measure pressure. Historically, these pressure measuring devices like manometers and barometers use mercury because it's a very dense fluid. Mercury vapors are not good for your health, so it's not used as frequently anymore. But that may be why you've heard inches of mercury used as a unit of atmospheric pressure. If in the weather forecast, for example, if they're talking about barometric pressure, they might talk about inches of mercury as a unit of pressure. So speaking of barometers, barometers are like manometers, except that they have a reservoir that is open to the atmosphere. And so the atmospheric pressure pushes down on this open container, and that pushes the fluid up into this tube. And so the greater the pressure, the higher the fluid level goes. And as I said, mercury historically has been the fluid most commonly used in barometers. The density of mercury makes it so that it's you can make relatively small barometers. You can make barometers, though, out of using other fluids. For example, this is a historic image of a barometer that used water. And you can see the top is way up here and the bottom is way down here. And this looks like it's 1, 2, 3, 4 stories tall, maybe 40 feet or so. That's not exactly practical. You can't exactly carry that around. So mercury works well because it's a dense fluid and you can use much less of it. But really you can make a barometer out of just about any fluid. So here's an interesting bit of trivia. I think it's interesting. When you drink through a straw, you probably think that you are sucking the fluid up through the straw and into your mouth. But really what's happening is you're sealing off the end here, and in your mouth you are creating a vacuum by removing the air from your mouth into your lungs, and that creates a pressure differential. The atmospheric pressure then goes into the can, just like a barometer, and pushes the fluid up the straw and into your mouth. So what I think is interesting here is that the fluid is actually getting pushed up the straw by the atmosphere. If we did not have atmospheric pressure, that wouldn't work. So in other words, you couldn't drink from a straw in outer space because you need that atmospheric pressure pushing in on the fluid to make it go up through the straw. Okay, we're now going to start talking about the idea of buoyancy. And essentially buoyancy is what makes things float. And so if we look at an object submerged in fluid that has some significant height to it, some delta H here, the top of this object is going to experience a certain amount of rho GH pressure at the top, and at the bottom it will experience a different amount of rho GH because the H is different. It's deeper into the fluid than the top is. And so there is a difference in pressure. There's more pressure acting at the bottom than there is at the top. And this difference in forces results in a net force acting up. And that force acting up is what we call buoyancy. It's the buoyancy force. So buoyancy is equal to the force from below due to the greater pressure at the bottom of the object minus the pressure at the top at the lesser height. And so mathematically we can call that rho G and then the force is acting on an area. If this is a cylinder with a circular top, we could call that the area A times the difference in height. Okay, so the difference in height we can just call delta H. And then if we take that area multiplied by the height, that's just the volume of the object. So the area of the top multiplied by the height gives us the volume. And density times volume equals mass. So the buoyancy force is equal to the mass times gravity. But it's important to note here, it's not the mass of the object, it's the mass of the fluid. So however much of the fluid would fill up this object, if we multiply that by the acceleration due to gravity, that tells us the buoyancy force. So things tend to float more easily in denser fluids because there's more buoyancy force. The Dead Sea, for example, has a very high salt content, which makes the water more dense than typical seawater, and people are able to more easily float in the Dead Sea because of its high concentration of salt, because the more dense fluid causes more buoyancy force. All right, I think I'm going to stop here because this next example here, the Archimedes example of using buoyancy to determine the makeup of a crown, is probably going to take a little while to explain, and I don't want to run out of time in the middle of it. So I'm going to cut this video a little bit short and resume with the next one.